This is All India Radio. Power of listening. Under this series, tonight we take you on a journey to the world of yet another magnificent facet of the traditional Indian knowledge systems. In this episode, we shall be focusing on the knowledge of trigonometry in ancient India. Our expert on the show is Dr. Shashikant Ananta Katre, Professor, Lokmanya Tilak Chair, University of Pune. Stay tuned.
Today we shall discuss development of trigonometry and geometry in ancient India. The first known geometer of India can be considered as Bodhayana, who was probably around 800 BC. Bodhayana was a follower of Krishna Yajurveda discipline in India. He has Bodhayana Shulva Sutras, which are part of Krishna Yajurveda, and he has 10 chapters in his sutras. The first chapter deals with geometry because he had applications in mind regarding Yajna Kunda or fire sacrifice, and for that the preparation of altars or Vedi, how these are to be done, that could be explained by principles of geometry. Therefore, at the beginning he explained important results from geometry. In fact, there are 519 Shulva Sutras scattered in 10 chapters. Out of them, the first chapter contains 117 sutras. These are written in short. These are statements of some theorems in geometry, as we shall see. In fact, the famous Pythagoras Theorem is also stated in these Shulva Sutras. The Shulva Sutras do not contain proofs of the results, but they are actually statements of the results which will be later on useful. To give you an example, I will consider this sutra from Shulva Sutra of Bodhayana. Samachaturashrasya akshanaya rajjuhu dvistavatim bhumim karoti. The problem is, you have a square and you want to construct a square whose area is 2 times the area of the given square. How will you achieve this? Now a layman thinks that because you want twice the original area, we should make each side of the square 2 times the original side, and then the area will become double. So it is stressed in such Shulva Sutras that this is not the right thing. So how to construct a square whose area is 2 times the original area? So for that, Bodhayana gives this construction. You take the square and consider Akshnaya Rajju. Akshnaya Rajju means slant rope, which is the diagonal of the square. And if you construct a square on that diagonal, that means the length of each side of this new square should be equal to the length of the diagonal. So then dvistavatim, that is 2 times bhumim, the original bhumi, that becomes now 2 times that. So if the original area is a square, then new area is 2 times a square, where a is the side of the original square. Now here actually you are using a particular case of Pythagoras Theorem, that is, you have for a square of the diagonal is side 1 square plus side 2 square, that is a square plus a square. So this is how it is used, and later on actually the Pythagoras Theorem is also stated in another sutra that we shall see soon. But there are various results about geometry in the Shulva Sutras. Just to give you an example, draw a circle whose area is equal to the area of the given square. Such problems are considered. Draw a square with the help of a chord alone. Draw an oblong, that is a rectangle. Drawing a rectangle means what? You should be able to write down the correct angle, right angle. All the angles of a rectangle, they are right angles. So how do you exactly get those corners as right angles? So that is explained in Bodhayana Shulva Sutra. How to construct the side of a square whose area is twice the area of a given square? that I have just now explained. Do the construction of a square for getting thrice the area. Then Pythagoras theorem. Then method of combining two squares. Combining two squares means you have one square, another square. Now we want a third square whose area is equal to the sum of the areas of these two squares. So how to construct that square? Means how do you get the side of that third square to achieve this? Similarly, convert a square into a rectangle of the same area. Convert a rectangle into a square. Convert a square into a triangle of equal area. Convert a square into rhombus. Rhombus is considered as a double triangle. That means you take an isosceles triangle and on one side you just take a reflection and you get actually two triangles on the two sides of that diagonal. So rhombus is considered as a double triangle in Bodhayana Studio Sutras. Turn a circle into a square of equal area. Now, why these problems were considered? Because they were doing yajnas or fire sacrifices. So there you wanted yajna kunda altars of the same area. So one yajna kunda will be circular, another will be of square size, and the areas of these two must be the same. So if you start with a square of side A and then you want to convert this into a circle, that means we want the radius of a circle whose area is equal to the area of the square. How do you get that radius? So Bodhayana gives a construction of this radius so that the result is achieved. Conversely, if you first have a circle, so if you have a yajna kunda of circular size, then we want the side of the square so that the areas of these two will be the same. Another thing given in these is the relation between diagonal of a square and the side of a square. The value of root 2 is required here, which we shall see soon. And then using these, he calculated altars, number of bricks required for various altars of different shapes. For example, falcon shape altar, chariot wheel, trough, tortoise, and cremation ground related altars. So these applications were there, and in fact the geometry developed by Bodhayana was for these applications to altars, yajna kundas, vedis, etc. Now there was also another treatise at that time which was called Surya Siddhanta. Now the original Surya Siddhanta is not available. Probably that was in the 6th century BC. But later on, Varahamira wrote this Surya Siddhanta in his own way, and that or its modifications are nowadays available. Now Surya Siddhanta also does trigonometry and geometry, and these are with the aim of application to astronomy. That means the motion of moon, planets, then what is the diameter of a planet like Mars, Jupiter. So for these calculations, trigonometry was developed and used. So let us look at Pythagoras Theorem. The theorem is described in this 48th sutra of Bodhayana Studio Sutra. It says, Dirgha chaturashyasya akshnaya rajjuhu parshvamani triyangmani cha yat pruthak bhute kurutaha tat ubhayam karoti. Now here, Dirgha chaturashya, that is a rectangle. Akshnaya rajjuhu means diagonal. So you take the diagonal or a rope stretched along the length of the diagonal of a rectangle. Now usually nowadays we write this theorem, Pythagoras theorem, for a triangle. Whereas in Bodhayana Studio Sutra it is written for a rectangle, but it means the same thing. So it says you take the diagonal, and this diagonal, what does it do? Parshvamani triyangmani cha. There are two sides of this rectangle. One is the base, another is height. So these two sides of the rectangle will give you some area. Now what is the area of a square? If you know one side, then the area will be the square of that side. That means side is A, area is A square. So this means square of one side plus square of another side is equal to the square of the hypotenuse of that right angle triangle or the square of the diagonal of this rectangle. So In this way, Pythagoras theorem is stated. It may be noted that Pythagoras was around 500 BCE and Bodhayana is considered at least around 800 BC, or his time may be before that also. It cannot be exactly determined. So the statement, I will repeat, a rope stretched along the length of the diagonal of a rectangle produces an area which the vertical and horizontal sides make together. Ubhajang karoti means together they do that. Now another thing in Bodhayana Shulva Sutra is how to calculate root 2, or in other words, how to get the length of the diagonal of a square if the length of a side is given to you. And we know nowadays that the length of the diagonal of a square is a root 2, a times root 2, where a is the side. So essentially you should know the value of root 2. Now this value of root 2 is given as a rational number, or an approximation to root 2 is given in the following verse. Samasya dvikarani. That means you want to make the area 2 times the original area for the given square. What you should do for that? Pramanam. Pramanam means the given side of the square. What you should do with that? Tritiyena vardhayet. Pramanam tritiyena vardhayet. That means if original side is a, add a upon 3 to that. But that's not enough. Tat chaturthena vardhayet. Tat chaturthena means 1 by 3 again divided by 4. So it is 1 upon 3 into 4. Okay. So a plus a upon 3 plus a upon 3 into 4. Now what happens? This becomes slightly larger than root 2. So you again make it less. So it says Atma Chatustrinsho Nena. Atma means whatever you have got. Chatustrinsho, that is 34. That part you take and you subtract that part. That means you should subtract a upon 3 into 4 into 34. And so the value of root 2 is 1 plus 1 upon 3 into 4 minus 1 upon 3 into 4 into 34. And that comes out to be 1.414215, etc. And this value of root 2 is correct to 5 places of decimal. Now there are some special quadrilaterals, rectangle, square, rhombus, and their properties were stated in this Shulva Sutra. Area of a square formed by joining midpoints of a square is half of the area of the original square, or midpoints of a rectangle. If you join them, you get a rhombus, and the area of this rhombus is half of the area of the rectangle. So such rules regarding geometry were given. There are some properties of triangle, circle, they are also given. Now Aryabhatta, for example, gives these things which are there in Bodhayana Shulva Sutra in different verses. So Aryabhatta in the 5th century wrote Aryabhatiya, and in that he has a verse Yaschaiva bhuja vargaha koti vargascha karna vargaha saha. Now this is in our modern language. You take a right angle triangle, then varga means square. Square of one side plus square of another side is equal to karna vargaha. That means the square of the karna or hypotenuse. So this is Pythagoras theorem, and in one line, first line of this verse, he gives the Pythagoras theorem. He also says Vrutte Sharasamvargaha Ardhajya Vargaha Sakhalu Dhanushoho. So this is another property which we study for chords in a circle. In any circle, when a diagonal perpendicular chord intersect, the square of the half chord is equal to the product of the two segments of the diameter. In nowadays, the value of circumference of a circle upon diameter is denoted by the Greek symbol pi. In those times, this notation pi was obviously not there, and this constant, that is for any two circles, this ratio circumference upon diameter is the same. That was understood, and attempts were made to find the value of this ratio. So what is the circumference for a given diameter? This question was answered, and the approximate value of this ratio was given by Aryabhatta in the 5th century. In a different way, this ratio is available in some applications in Bodhayana also. But these values in Bodhayana Shulva Sutras were slightly different in different applications. For example, the value in one application comes out to be 3.088. Sometimes it is 3.12, etc. But Aryabhata gives the value correct 4 places of decimal at that time, which is a great achievement. The verse of Aryabhata in his second part, that is Ganitapada of his book Aryabhatiya, is the following. Chaturadhikam shatam ashtagunam dvashashtihi tatha sahasranam ayutadvaya vishkambhaha tasya asannaha vrutta parinaha. Let us see the meaning of this. Chaturadhikam, that is add 4. Shatam ashtagunam. So Chaturadhikam shatam, 4 plus 100, that is 104. Ashtagunam, it becomes 832. Dvashashtihi, that is 62. Tatha sahasranam. Sahasra, that is 1000. So 62,000. Now 832 plus 62,000 becomes 62,832. Now he says Ayutadvaya Vishkambhasya. So Ayutadvaya means what? Ayuta means 10,000 multiplied by 2. Dvaya, 2. So what is that? It is 20,000. Now 20,000, if that is the Vishkambha, that is diameter, then what is the circumference? Vrutta parinaha, that is the circumference. So he says tasya asannaha. Asannaha means close. So if the diameter is 20,000, then the circumference is approximately 62832, and therefore the ratio comes out to be 3.1416. This value is correct to 4 places of decimal, but even then Aryabhata makes it clear that this is not the exact value of the ratio. He says asanna, that means it is close to that. So there was an understanding of this fact that the value 3.1416, although we say it is correct to 4 places of decimal, it is not exact. That was clear to Aryabhata. And incidentally, the same value was given by Bhaskaracharya in his book Lilavati. Bhaskaracharya was born in 1114, and that is in the 12th century, and he gave the value of pi as 3927 divided by 1250, which is again 3.1416. He has given the value in the least form, a rational number in the least form, that is no common factor is there. 3927 divided by 1250, there is no common factor in the numerator and denominator. And he also says that this is close approximation. And he also says for practical purposes, you do not have to use this complicated 4-digit numerator and denominator. You can be satisfied with a simple approximate value 22 upon 7. This value 22 upon 7 nowadays we use in high school. Of course, are there better approximations to pi? That's the question. And in India, Madhavacharya, he was a mathematician of 14th century. He gave a value of pi correct to 11 places of decimal. In fact, he also gave an infinite series for pi. His infinite series is very interesting. It says pi by 4 is equal to 1 minus 1 upon 3 plus 1 upon 5 minus 1 upon 7 plus etc. So you see alternate plus minus signs are there, and denominators are 1, 3, 5, 7, etc. These are odd numbers. So let me repeat it. Pi by 4 is equal to 1 minus 1 upon 3 plus 1 upon 5 minus 1 upon 7 plus etc. This was called Newton-Gregory series, but now it is called Madhava series or Madhava-Leibniz series, because it was now understood that Madhava or Madhavacharya, he gave this formula in 14th century itself, much before Newton and Leibniz. It is also interesting that the sine and cosine values can be obtained by another series which was given by Madhavacharya, and these series for sin x and cos x we now study in our calculus courses. For example, the series for sin x is 1 minus x square upon 2 factorial plus x raised to 4 upon 4 factorial, etc. And similarly, the series for cos x is x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial minus etc. So these series are studied in calculus courses and these were already given by Madhavacharya. Only thing is Madhavacharya's books are not available, but his Shishya or students, they wrote books and they said Madhava Vadati. So Madhava said so. That's what they wrote. And from that we know this work of Madhava in the 14th century. The values of sin x, they were also given in our ancient treatises. And probably for the first time, these were made available in Surya Siddhanta, which was probably written in 6th century BC. Now, this work in Surya Siddhanta was used by later authors such as Aryabhata. And in Aryabhat, he gives the values of sine of theta. Theta is an angle. He takes between 0 and 90 and divides 90 into 24 parts. So, 90 upon 24 is the angle of 3 degrees and 45 minutes. And he says sine of this angle 3 degrees and 45 minutes is 225 upon 3438. Then the next angle he considers is 2 times this. That means 7 degrees 30 minutes. And sine of 7 degrees 30 minutes is 449 upon 3438. Like that he goes on and he gives the sine of 24 angles, that is multiples of 3 degrees and 45 minutes. And 24 times this angle is the angle of 90 degrees, and this angle, for that the sine is 1. So sine of 90 degrees is given as 3438 upon 3438, and that is 1. That's what we know. And for the intermediate angles, for example, what is sine of 1 degree, 2 degrees, etc. And that can be obtained essentially by interpolation. The idea is that if you remember these 24 values of sine ratio, then you can get the remaining sines also. You don't have to remember these. As per requirement, you can calculate this. Also, another important topic in trigonometry that was treated in these ancient books of Aryabhata, Bhaskaracharya, etc. is heights and distances. We study this thing in the high school level, and for example, we find out the height of a Deepastambha or light tower from a certain shadow. Or sometimes you have to find the length of the shadow, as is the case in the case of eclipses. The applications such as time of the eclipse or various applications such as diameter of say Saturn or all these planets. So such problems when you have to deal with, you have to use this idea of heights and distances. And there are 2 verses in Aryabhata's work. These are, the first one I will tell you, Shanku Gunam, Shanku Bhuja Vivaram, Shanku Bhujayoho Vishesha Dhrutam, Yallabdham Sa Chaya Deya Shankoho Swamulad Hi. Now here you have a light tower and there is a pole, and because of that light tower you get the shadow of the pole. Now if you know certain things about the pole and the light tower, that is distance between them or heights, etc., then we can calculate the shadow. Or if you know the shadow, you can calculate the height of the light tower. So the verse says Shanku Gunam. Shanku means that pole. Shanku is the pole, and you multiply by the height of the pole. What you should multiply? Shanku Bhuja Vivaram. That is the pole and the light tower, the distance between them. That you should multiply by the height of the pole. So it is the product of these two. Now what you should do after that? You should divide this product by Shanku Bhujayoho Vishesha. So you subtract these two heights. Height of the light tower minus height of the pole. So that difference you take and you divide the previous product by this. So in a simple mathematical formula, D into H2 upon H1. D means height of the pole. H2 means Shankubhuja Vivaram, that is distance between pole and the light tower, and divided by H1. H1 is the Shankubhujayoho Vishesha. So that is difference between heights of the light tower and the pole. That gives you the length of the shadow. So let me just say it again. Multiply the distance between the pole and the light tower by the height of the pole and divide it by the difference between the heights of the light tower and the pole. That gives the length of the shadow. And the next verse of Ganitapada gives us the formula for height of a light tower using the shadows of two poles of the same height. So what we are doing is, on one direction you keep two poles of the same height, and from their shadows you are able to calculate the height of the light tower. And that is what we do in trigonometry. It's an application of trigonometry. So certainly, as we see, these two texts in our language, we call them texts. One is Surya Sutra of Bodhayana and then Surya Siddhanta. They do different applications, and for that you require some trigonometry and geometry which is developed initially and that is used later on to get the required results. They also required areas and volumes, and some formulae are also given in Aryabhatta, Ganitapada and Bhaskaracharya's Lilavati. So let us discuss these in short. The area of a triangle is 1/2 base into height. This is stated by Aryabhatta in Ganitapada. Tribhujasya phalasariram. Tribhuja is triangle, its phalasarira is area samadala koti bhujardha samvargaha. So koti is height, bhuja is base, ardha 1/2. So 1/2 base into height. However, Aryabhatta gave the volume of a tetrahedron. That formula unfortunately was wrong. He gave the formula 1/2 area of base triangle into height. That was wrong. It should be 1/3. But this correction was done by the next mathematician, that is Brahmagupta, who was in the 7th century. Actual formula is 1/3 base into height. Now, what is the area of a circle? That was also given by Aryabhatta. Samaparinahasya ardham vishkambardhahatam eva vruttaphalam. So circumference upon 2 multiplied by diameter upon 2. Diameter upon 2 means radius. So this formula gives us 1/2 into 2 pi r in our language into r. That is pi r square is the area of the circle. Now he gave the formula for volume of a sphere, and unfortunately this formula is wrong, but it was later corrected by Bhaskaracharya in the 12th century. In between also mathematicians tried to correct this formula, but they were not successful in this. Bhaskaracharya in his Lilavati verse 196 gives us the formula for area of a circle. Vrutta Katre paridhi gunita vyasapadaha phalam yat. Here he gives area of a circle is pi r square. Kshunnam vedaihi upari paritaha kandukasyeva jalam golasyevam tadapicha phalam prishthajam. So prishthajam surface area, golasya sphere, it is kshunnam vedaihi. Veda means 4. So previous answer pi r square you multiply by 4. That gives 4 pi r square, and that is the surface area of a sphere. This is the correct answer given by Bhaskaracharya. Vyasa nikilam. So you multiply this by Vyasa, that is 2 times radius, and then Shadbhiri Bhaktam divided by 6. That becomes the volume of the sphere. Bhavati niyatam gola garbhe ghanakhyam. That's what he says in verse 196 of Lilavati. And these are correct formulae by Bhaskaracharya. The proof of this formula for volume of a sphere was given in the 4th book of Bhaskaracharya. Bhaskaracharya has Siddhanta Shiromani, which has 4 parts. Lilavati means arithmetic, Bijaganit, that is algebra, then Graha Ganita, that is astronomy, and Goladhyay, it is spherical trigonometry. So there the proof of the volume of a sphere formula was given by Bhaskaracharya. Actually, this was this formula for volume of a sphere or surface area of a sphere was first given by Greek mathematicians, and that was correct. In India, it took us some time to get the correct answer. But the interesting thing is that Bhaskaracharya's proof was as per the methods of calculus which we study nowadays. And Madhavacharya also, he gave infinite series for sine, cos, and value of pi in terms of infinite series. So these infinite series were first considered in India, and Bhaskaracharya and Madhavacharya, therefore they are called as pioneers of calculus in India. Thank you.
You heard this episode of our all-new series on traditional Indian knowledge systems, Power of Listening. Our expert on the show was Dr. Shashikant Ananta Katre, Professor, Lokmanya Tilak Chair, University of Pune.